All right. So, hey, Akash, welcome to the podcast.
Yes, thank you so much for having me. Really appreciate it.
Yep. And thank you so much for agreeing to do this. I know that, you have like a very busy schedule and, you're working on multiple things. So, first of all, thank you for taking out the time and agreeing to do this. And I'm excited to talk through, about your background, your journey, starting through your PhD experience and then probably going all the way into what you're doing right now.
Love it.
So, yeah, why don't you just, probably just go ahead and introduce yourself for the audience?
Of course, yeah. So my name is Akash, and I'm the co-founder and CTO at Silimate. I'm originally from Pittsburgh, Pennsylvania, so East Coast, and grew up pretty close to CMU. And my parents are both professors at the University of Pittsburgh. I did my undergrad at Princeton, and I majored in EE and minored in physics and CS. And it wasn't really until graduate school that I got into semiconductors, actually. So when I went to Stanford, I was very interested in sort of looking at new types of nanotechnologies, and I ended up working in a research group where we were working on chip design. I also spent a bit of time during my PhD at NVIDIA and Synopsys and working on EDA tools, and so that's how I got sort of into the EDA space from chip design. And then I co-founded Silimate with my co-founder Anne right after the PhD, and have been working on that since then.
Wow, I mean that's quite a vast experience, Akash, I have to say, and there's so many interesting things which I want to talk about and probably dig deeper. But
Yeah.
I think the first thing which I want to focus about your exposure to chip design. I mean, you touched upon it in your background, but how did you figured out that hey you wanted to do this, and how did you ended up choosing going to Stanford for a PhD in chip design and then exploring various other parts of it throughout your PhD journey? Like, would you want to share a bit more details of your journey throughout?
Of course, yeah. In undergrad, I had a very kind of broad set of interests, I would say. So I studied, a bit in physics. I was really interested in computer security. I've always been sort of a hacker by nature. I really like reverse engineering things. And so I actually did my undergrad thesis on security and privacy. And I basically really enjoyed doing that. And I was trying to think about, like when I go to graduate school, is this what I want to keep working on? And I kind of, I really love security and privacy stuff, but a lot of it feels like a cat and mouse game. Like you fix, you find some bug, and then you fix it, and then, it's kind of felt more difficult to have sort of a lasting impact on the field. And that's my take. I think others have, different takes on this. But when I
Sure.
went to grad school, I sort of started rethinking through all the courses that I'd taken and thinking about, how do I tie all this together, thinking about what I wanted to do. The goal when I went into the PhD was how can I wanted to find sort of, I was very interested in unconventional computing, thinking about integrating like new technologies into the chips that we have. And
Mhm.
when I started applying to grad schools, I was looking through all of the professors working on something that I deemed unconventional in some way. And eventually, I ended up going to Stanford, where I aligned with a new professor, Priyanka Reina. So I was actually her first student to graduate out of her group. And
Oh wow.
so she had just finished at MIT and had been working at NVIDIA for a few years and came to Stanford wanting to, do very similar stuff. She was very interested in, how can we build faster computers that are better? And she was more, I would say, more interested in looking at it from like the silicon perspective. And then I came in and was like, well, would you be interested in thinking about some, sort of some unconventional computing methods? And she was very open to that. And
Mhm.
so we started, yeah, I started working with her. It was a really cool experience working with as her first student. One of the great things about that is I think, for a young professor, a lot of the incentives are very aligned, right? They want to publish, they want you to be successful, they want you to work on projects that you're interested in, but are interesting to them as well, right? And
Yep.
so all of these things together, I think, made it a really great experience. And maybe I can talk a little bit about what I worked on in my PhD.
Sure. Yeah. Yeah. Please go
Yeah.
ahead. And then
Okay.
probably you could cover your thesis as well. Like, what was
Sure.
it
Sure.
majorly about? Yep.
Yeah. So in my PhD, I started off working on how we can make reconfigurable technologies like FPGAs or CGRAs, which are kind of like a coarse-grained reconfigurable array, how we can make them more efficient. And I was looking at the why are FPGAs less efficient than ASICs? And the answer is really the reconfigurability, right? And so I was really interested in well, is there a way that we can improve the reconfigurable nature of these devices, right? And so I was looking at these I would say, kind of a very unconventional idea, which is use mechanical switches, right, to switch between different to implement sort of the connection blocks and the switching boxes, right? Those that make up the FPGA fabric. And so I was looking at nano electromechanical relays, which are basically relays that you can, they're similar to a transistor in a lot of ways, but they basically, when you apply, a voltage, you get it to clamp down, and it can connect two terminals, right? Very similar to a transistor in a lot of ways. The difference is that, you can implement them on top of your CMOS, right? So they go on top instead of inside of the circuit. And I found that topic very fascinating. We found that, if you implement these, you can get like a 25% area reduction, like a 10% power reduction, something like that.
Oh, wow.
Some very interesting numbers. And after that project, I was very interested in resistive RAM. So resistive RAM is a type of non-volatile memory. You can integrate it directly. So most of the foundries today, I think Global Foundries, TSMC, Intel, have offerings for this, especially on older technology nodes like 16 nanometer and above. But basically, this is it's a type of non-volatile memory similar to flash, but you can embed it directly into your silicon devices, right? So this is on chip, and that makes the memory bandwidth very high. So you can do a lot of really cool things with that. And so I was focusing on how do we make these memories more efficient? How do we store more bits? So basically, I started looking at some techniques that were similar to flash memory, where you can store multiple bits inside of a single cell. So the concept of resistive RAM is it's like a programmable resistor, and I was looking at how you can like tune that resistance to store different encodings for states. And so I spent and then straight from that, I went right as soon as I defended my PhD. I started the company within. Yeah.
Wow. I mean, that's probably very interesting. So, one question about the resistive RAM I have, like how big were those? I mean, you said that those are on-chip memories. So I'm just wondering, like, how big were those? And like, as part of your entire PhD journey, were you also able to probably tape out some of these ideas and see them in action in real silicon?
Absolutely. So I'll answer your first question about the size of resistive RAM. So you can make resistive RAM with sort of it's hafnium oxide, which is the same that's used for gates, right? So that's a really cool thing about it, is that you can kind of put it into it's very compatible with the CMOS process.
I see.
Because of that, you also can use standard lithography techniques, right, for it. And so you can get for a single RM cell, it's just a square, right? So you can just make it a 4F squared thing, which is basically the feature size of your technology. And so I was looking at it in 40 nanometer TSMC technology. That was what I did when I was looking at the technology I used in my PhD was the 40 nanometer TSMC technology. But the interesting thing about those is it's not actually limited by the resistive RAM. So they usually have a control transistor, right? That is basically, able to control whether or not that RAM cell is selected, right? And so this is called the selector transistor. And the selector transistor actually takes up more area, right? So that is more limited by like how much drive strength you need to send to your cell. And you typically, so when we were working with TSMC, they picked that for us. I also did one tape out with this foundry called Skywater. And so we actually helped them bring up their resistive RAM process at Stanford. So we basically were giving them a lot of guidance on how to build this process based on the research that had been done at Stanford in the nanofab facility. And there we had to optimize the size of the selector ourselves, which was very challenging, I would say. But we eventually got it. And so I did, in my PhD, I actually did 3 tape outs. And one of them was with Skywater, and then 2 of them were with TSMC. And the first one was just like the test chip that we did to bring up the process, the
Right.
RM process. And we did like a lot of, configurations where we were trying to test different sizes of the cells, selectors, etc. The second chip was one I actually did collaborated with Haitong Lee. He's now a professor at Purdue, and
Sure.
we were working on basically building a one-shot learning device using RM as sort of as a ternary content addressable memory. So this means that it basically has 3 states, right? And you can basically do like a nearest vector search using this device. And we actually ran some machine learning applications that use that on top of it. And then
I
my
see.
third tape out was the one that I did in my dissertation, which was related to the multi-bit concept. So this concept of how many bits per cell can we store inside of a single RM cell. And that was super interesting. Probably my favorite project because I actually got to do the full thing end to end. Right. The other 2 I
Yep.
was involved in the process, but I wasn't the main author on that. And that one was one where I was the primary author, and I really got to see everything. So that chip was I wrote the digital spec for it. I wrote verification test benches, and I tried to write them in UVM style, so I could learn. I basically tried to learn everything along the way. I also collaborated with one of my colleagues on the analog mixed signal parts. So basically, a lot of the circuitry for the RM itself was, it kind of blurs the boundary between digital and analog side. And we had to interface things between those. And so that was cool. But then in addition to that, I did the full physical design process, right? So doing synthesis, place and route, making sure that all the sign-off checks went through, right? And even better was once we got the chips back, I actually designed the PCB to help bring up the chip.
Oh wow.
And I did that.
That's taking it to the next level, Akash, I would have to
Yeah.
say. And I'm so envious that you got to experience all of that. I've been meaning to try out Skywater, MPW when those were a thing back then. I've been, meaning to try out all of the different open source, physical design tools, because that's something which I have minimal exposure as part of my, day job, and I just don't find any time to do that. And you're so lucky that you had the opportunity to go through the entire process, and even up until like getting the PCB out. That's like completing the entire circle. And I'm sure that you would have had the opportunity to learn a lot, going through that process and seeing it come to life. Yeah, I mean that's
Totally.
absolutely amazing. Yep.
Totally. And so I designed the PCB. Actually used open source tools for that as well. I used the KiCad, which is the open source
Yep.
PCB. I actually asked my advisor, like, should we just outsource this? Should we just get, like hire someone to do the PCB? And she's like, I think you should do it yourself. And I actually am so glad that she did that. She made me do it. It took some time, obviously. It took me like a week or 2 to learn how to do PCB stuff and how to actually design this to do exactly what I needed it to do. But I'm actually so grateful to her for making me do that, because, and actually, everything in the process, like, she was like, you can learn how to do this the right way. And I kind of took that to heart and basically tried to learn how to be the full stack chip designer, right? And I think that's it's something that's so underrated, right? Like when you see the full stack, it really starts to make the full picture starts to make sense, right? Like you start thinking about synergies between different layers of the stack, right? And how you can optimize. When you're thinking about optimization, you have to think about how each step affects every other step, right? And
I agree.
I think this is one of the really cool things about doing a PhD, and one of the reasons I strongly recommend it to anyone who's interested in learning just everything there is to know.
Yep. No, I absolutely agree on that. I think if you can get the chance to experience the entire cycle, that just makes you a better engineer overall. Instead of focusing on, one problem at a time, rather than going all across it, all beyond it. Obviously, it's going to take more time. You have to learn and unlearn a lot of things. But, at the end of the day, you would become a better engineer, and you would have like a better, bigger picture, and, then make calls as to where, this particular logic best fits, or way to make different optimizations, just like you said.
100%.
Then, yep. That's great. So, but I think that your experience, during your PhD was a lot about, the physics side of, semiconductors. And you did mention that you actually got a chance to write the digital spec for one of the projects, and you also wrote the test bench infrastructure and stuff like that, where you actually got a chance to learn about all of the different, the UVM methodology and how do you write RTL and stuff like that. So how was that exposure, and how did you find that? And then eventually, like, when did you decide that, hey, after my PhD, I want to, probably do a startup or something, like, because that's completely like flipping off, like, from being in a researcher mode to being in a, place where you have to build things which are, not just cool from a scientific point of view, but they
100%.
actually have real value to real users who's going to pay money for that. So how did that transition happen for you over, the last couple of years?
Sure, I can tell sort of maybe the story of it, and then also some reflections, I guess, looking back. Um,
Sure.
yeah, so during, while I was doing the chip design process, I found so many inefficiencies, I would say, in the process, right? At every stage, you're kind of, struggling a little bit, right? And this is why it takes so long to get a chip out the door. I think there's a lot of, I came from, and I think it's really great that I came from a software background, so I can. Otherwise, you might think that this is the norm, right? And that this
Yep.
is like the way
Yep.
that software, But one of the cool things is I like came from a software background, and then started seeing all these inefficiencies, and you immediately are like, whoa, this is like going back in time a little bit, right? When you go into the hardware world,
Right.
everything, all of the tools run slower. They all, you know kind of give you outputs that are tricky to interpret, right? You have to they don't give you a lot of guidance by default, right? They just try to do the job as well as they can. And Synopsys cadence tools, they do a great job at optimizing for PPA, but I think on the part of giving feedback quickly and helping you like improve your designs from the one level higher than the actual collateral, right?
Right.
Is a little bit lacking. And so I started getting really interested in that, and I first worked at NVIDIA, and I was actually working on their internal EDA methodology. So they have a very large, relatively large for a company, internal EDA methodology team. And it was very
Hmm.
inspiring because I think they had a very, very strong approach to building EDA tools. They're very well architected. They were very extensible in the sense that you can build new EDA tools on top of them. And in fact, during my internship there, I built a new EDA tool that helped optimize one part of the synthesis process very well.
I see.
And after that, I was basically sort of thinking about, okay, well, this field seems really cool. And so I went the next summer and I asked my advisor, do you know anyone at Synopsys? And she actually knew um, someone who ended up becoming my manager there. And
Hmm.
I went and worked at Synopsys the next summer, working on their AI for EDA tools. And so that's sort of how I transitioned into like not just chip design, but I got really into this EDA thing. And when I was at Synopsys, I loved it there. It was a really cool experience. I got to work on their the DSO.ai product at Synopsys, and I was looking at some new methods for applying it, and I ended up getting a publication, a patent from the stuff that I worked on there, which was really cool. And
Hmm.
that really inspired me to want to do, to try to take these ideas to industry, but a little bit faster than I could through, trying to go
Right.
to a big company. And
Right.
so that fall, right after I did this was in 2022. In the fall of 2022, I started looking for kind of a co-founder to work on this startup with me. And
Mhm.
Anne, so who's my current co-founder and the CEO of
Yep.
Silimate, I had known her for a long time actually, and she was sort of one of the top people who I had in mind. Because we had actually been class projects. We'd known each other since like 2019 or 2020, and
Sure.
yeah, she's like she had been working at Apple for 4 or 5 years at that point, and was super like very expert in the front end design process, and also
Hmm.
very interested in starting a company. So I think that all of the stars sort of aligned there, which is really cool. And we did this class at Stanford called Startup Garage. This is in the business school,
I
and
see.
we basically spent that entire course just talking to users. We didn't build anything. We were just trying to understand, what is a good problem to be solving in the space? How do people think about it in industry? And we tried to make a lot of connections, right? And meeting a lot of people, some who became our eventual customers, which is really cool. And towards the end of that course, so we kind of had an understanding of like, wow, this space, everyone agrees that there's a problem, and that there's a lot of opportunities for trying to fix this. So then we started, taking some of our learnings and trying to raise money, basically. So we started looking to try to raise money for our company. And we basically were talking to a bunch of VCs, and we're actually starting to get preempted for rounds. So we're starting to, get offers, and then we got into Y Combinator. We applied to a bunch of accelerators as well. We got into Y Combinator, which was a dream come true for us. And then everything, it was very crazy from the moment we got into YC, because at that point I still had 6 months of my PhD left, and the Y Combinator was starting in June of that year. So we got in around March, I would say, or March or April, and so I had to go to my advisor and say, hey, I got into this accelerator. I have $500K in funding, and I want to start doing this in June. Is there any way we can make that happen? And her response was, whoa, you're working on a startup? Okay, I guess that's cool. And you can defend in June if you'd like, but you need to get all your work done, of course. We're not cutting any of the scope of your thesis for that. So the funny story is, I think I'm now sort of a legend in the Allen building at Stanford, because I would sleep on the couch there basically like every night, 6 or 7 hours, wake up and just immediately get back to work. And I was basically, we put the startup on pause for like 2 months while I was like wrapping up my PhD. Anne was sort of doing some of the logistical side of things, trying to get, the company incorporated, etc., while I was full focus, just trying to like complete my PhD. And I remember like 3 weeks, we were like 2 weeks out, and there was still so much to be done before my defense date. And my advisor was like, maybe we should do this like later. And I was like, no, we have to do this. But eventually I ended up getting everything done by the defense date. I defended it, went very smoothly. And the interesting thing was, firstly, the Stanford graduation was actually the day before my defense, which was kind of strange. So I actually, my parents flew in, and we did the whole like walk on stage and stuff. And then the next day I went and defended. So it was kind of an interesting order. But even more interesting is that after I defended, it was actually the same day that the Y Combinator retreat started. So I defended, and then basically I drove straight from my defense in my suit and everything to the Y Combinator retreat, which was in, I think, either Napa or Sonoma. I can't remember now. But I get there, and so we're basically, I'm like in the middle. It's in the middle of this talk where Gary Tan, who's the CEO of Y Combinator, is talking, and I like walk in, and basically immediately like the security comes, and they're like, whoa, who's this guy in this suit? Some like VC spy. And then I'm like, no, I'm just a founder, And eventually they sorted it out, so it was okay. But
wow, that's one crazy story, Akash. I have to say that. But yeah, congratulations on first of all getting that patent at working at Synopsys, and then defending your PhD alongside getting into YC. It's a great mix, I have to say. And then we don't hear such stories in the hardware world. I mean, probably it's more common in the software side of things, but definitely not in the hardware world, where people are defending their PhDs and then going straight into YC and trying to co-found a startup company. And I mean, so crazy story, first of all. And I can't imagine like how much pressure you must have been under when you would have like those 3 or 4 odd months to defend your PhD, get all the work done, and then even work on startup on parallel. So kudos to you, having made it so far. And so let's talk more about your YC experience, your experience working with Anne Wu, and how did you come up with the idea of Silimate, and what exactly is your product which you're trying to build there?
Yeah, absolutely. So YC
Hmm.
was a really cool experience. I think one of the best things about it is you kind of see a lot of other, like even more useful than just the advice, which is, in my opinion, the best startup advice in the world, is actually just seeing the other kind of startups around you, right? And they're all very ambitious, right? Really pushing,
Right.
pushing forward super aggressively every week, right? And they're,
Hmm.
you see all this and it inspires you in some way, right? And I think that
Right.
was probably the biggest value out of YC actually is, firstly just kind of showing us the benchmark of like what a good company looks like, right? And
Yep.
it's all around you and you feel it. And yeah, and I think so that was really cool. During YC, we spent a lot of time trying to figure out exactly what we were going to work on, and
Hmm.
we tried a bunch of different ideas, and we basically talked to a lot of users, and it took us a while to figure out exactly what we were working on, and we ended up at the end of it during the demo day, we basically presented sort of the first cut, which probably looks very different than what we do today.
Right.
And
Right.
yeah, and we were able to successfully, another superpower of YC is it makes your seed raising your seed round very straightforward, I would say,
Yep.
because you have a demo day. It's a forcing function for the investors. It's a very natural point for them to
Hmm.
come in and say, oh, here's, I'm interested in this space you're working on. Here's some money to go work on that. And so we raised
Right.
very quickly. We were able to close the round in 2 weeks, and so I'm very grateful for that because fundraising is never the goal. It's always a means to an
Yep.
end, right? And we're very eager to get back to work on the product. And
Hmm.
so yeah, maybe I can talk a little bit about Silimate and what we do now.
Yes, absolutely. Yep.
Yeah, so Silimate, it's the co-pilot for chip designers, and that's a very vague, term. But specifically what we do today is we find and fix functional and PPA issues in your design. And what that means is, we can make estimates of, your power performance area and highlight bottlenecks. And then in terms of the functional correctness, we can pinpoint and triage issues that are in your design. And we're mainly focused on pre-synthesis. Today, we actually have 10 plus companies using our tools. Tenstorrent is also a
Hmm.
customer, which is great.
Yep. Yep.
And yeah, it's been very interesting. Our long-term goal is really we want to go, make the process from spec to RTL very easy, and we want to get that process, mostly using natural language and have AI do the most of the job there. And so that's sort of our long-term North Star, I would say, for the company.
Sure. So yeah, let's talk a bit more about the product which you're building at Silimate. So you mentioned that it's a pre-synthesis product. So what does that exactly mean, and how does it actually helps you give the PPA for, let's say, a small RTL block which we are trying to work on and improve on timing, let's say, for one. So does that mean that if we run the tool on top of it, will it give us a timing report and which parts are expected to fail, and what is the error margin there? Like if I were to do the actual synthesis, place and route, and the entire PD flow, and if I compare the end of the reports from there with the reports which are produced using your tool, how do they compare?
Yeah, so we our tool does it gives power performance area estimates and gives you some ways of investigating those. Again, it's not going to be exactly the same as what you see from a synthesis tool, but the idea is really to highlight the bottlenecks, right? And
Right.
so what we try to do is show people, where can I improve my design? Where can I maybe insert a pipe stage? Where can I, optimize the way this logic is to reduce area or something so that it can fit
Hmm.
within, the margins that I have for my block,
I see.
optimize power in the same way. And
Hmm.
in terms of correlation to tools, I think it's probably like we don't quote specific numbers because it varies between different
Yep.
technologies. But the idea
Yep.
is we can also give feedback on things that are tool independent, right? So things like logic levels, right? The number of
Hmm.
instances, and these are
Hmm.
typically independent of the technology that you work on.
Right. I see. I see. And how does the like the artificial intelligence or the LLMs fit into this product? Like, what is the role which they play? And I know that you are very active in the open source community. Also, you've been making patches which are going and getting accepted onto the main repositories. Also, so like, is that tool like? I know it's called Precursor. So is it based on top of an open source tool where you've added like a bunch of stuff and the LLM part to it, and then it
Yeah.
tries and gives you like the entire PPA estimates which you're talking about?
Yeah. Yeah. So all of our tools are, we build on the shoulders of giants, right? And
Right.
so we build on open source tools. We also use this front end platform called Verific that they do
Hmm.
basically system Verilog parsing and stuff. We don't try to reinvent the wheel there and try to reuse as much as possible. And anytime we do that, we always give back any bug fixes or enhancements, like small enhancements that we have that are not our secret sauce, so to speak, right?
Yep.
Always give those back. And so uh, our tools, they basically, I would say Precursor is more of a, like, it uses like more traditional machine learning models, right? And that's how it's able to do some of the predictions that it does. And then
Hmm.
we use LLMs as well, and LLMs
Sure.
are for firstly for our functional correctness tool, and we use them
Mhm.
to basically understand things about the spec, things about the RTL, things about the test bench, right? You sort of have these three, and you're trying to align them, right? And
Yep.
the point is that there's often a lot of ambiguity in what is supposed to be happening, right, in a chip design. And so
Hmm.
LLMs are very powerful because they really deal well with ambiguity, or relatively well. This is something that you know you never have. You often don't have a written formal spec of like what is supposed to be happening in your design, right?
Right.
Um, and so an LLM is really great because it can actually look at these three different instantiations, right? Your written spec, your RTL, and your test bench, and really try to infer
Hmm.
what should have been happening based on its understanding, like a more semantic understanding of the design,
Yep.
if that makes
I
sense.
see.
And of
Mhm.
course, it's sometimes wrong, and so that's why you need to confirm, validate assumptions, right, against a
Right.
human. And sometimes even those, just unearthing what those assumptions are, can be very useful for a human designer. Like, oh, this is an assumption that we hadn't never written down anywhere, but it's something
Hmm.
that we need. Oh, this state is never accessible because this it's in this mode where this doesn't happen, right, or something like that.
Right.
And so all of these things are sort of very, I think, very fertile grounds for LLMs to come in and deal with the ambiguity and help solve some of these problems, right, that were previously not possible to be solved.
Yep. No, no, I absolutely agree on that. And as a matter of fact, I've had like two other co-founders on this podcast who are also working in the similar space. So yeah, I know it's Karthik who is trying to do it with formal and as well as the functional correctness. And then I had Kaylee who is also trying to do the same thing. Where he's building like a AI verification agent and stuff like that.
Yeah,
And I think. And then your functional product which which you guys are trying to build in Silimate. So the idea is, I think, the same, where you want to take in all of the information, then try and figure out what should have happened and why this particular thing failed, which is great. I mean, that's something which absolutely did not existed in the
100%.
last couple of years or something. And seeing it come to life, I mean, I've tried your tool also, and I've seen that, hey, it can point to a bug or it can point where it is, which is of great help. And I can see that a lot of verification engineers would be happy, because a lot of times you spend times figuring out where the exact spec is or where that particular code is within the RTL or the test bench. So all of that, if then if that can be abstracted away, you would be saving a lot of hours and a lot of debug effort which goes into building silicon. Because it's true that about 70 to 80% time is spent in verification and debugging. So if you can kill that, you're actually getting chips faster.
100%.
So which is a great idea. And I think both of your products are trying to do the same thing. One is targeting more of a, I would say, like a micro architectural level slash RTL design level, where you're trying to improve on PPA. Because I've worked with design where in order to get a timing feedback for one simple change, it can take anywhere up to a week to, even more than that if it's even bigger. So if you can get that quickly, so I'm not sure like how long does your tool take? Let's say if something were to run like a 7 days to get like the full CTS report, how long would your precursor tool will take to give you like a rough estimate as to whether this particular change would be helpful or not?
That's a great question, and it does vary a lot, right? So
Mhm.
the goal is really to give real-time feedback, and especially on smaller blocks, right? So for small blocks where you're working on, a particular module, it can give you like for more of the like leaf nodes, right, in the module hierarchy, you can get them
Mhm.
like near instantly, right? So we aim for like less than 10 seconds for those. And then
Wow.
for full designs, of course, it's not going to be, there's a lot of, hierarchy to process, right? There's
Right.
all this stuff. It we target like speed ups of 52,000x, right? And so this is sort of
Mhm.
like our targets that we shoot for with every customer, and we
Right.
tend to see around that. And we see that there's lots of different ways that you can integrate the tool. You can use it as a co-pilot. You can also integrate it as like a tool that can go into your CI
Mhm.
flows or whatever.
Yep. Yep. No, that makes sense. And I mean that's absolutely great. I think I'm very interested to know more about how the internals of these two tools have been come up, and probably going to ask you a bit more questions. But first of all, I would want to talk more about your success stories. You said that you have like approximately 10 or 10 plus companies which are using, and have you had instances where those came back and said that, hey, precursor gave me this data which would have taken 7 days to actually get it, and using that data we were able to get this RTL change or get this timing fix done in probably a day, otherwise which would have taken like a 10 or 2 weeks or something like that? Have you had those instances by now?
Yeah, yeah. We recently had an instance like that with actually one of our pilot customers that
Hmm.
that ended up converting to a full time. This was a very large public company, but basically there were
Okay.
designers that were using the tool and they were
Hmm.
seeing like really good, results. They were like, wow, this just like helped me find exactly where I should, insert some pipeline stage or do some optimization,
Right.
right? And it helped us close the deal really quickly, like much faster
Wow.
than we usually do. And it's basically like
Right.
we see that this is exactly, it's typically this aha moment that you're talking about that
Hmm.
ends up
Hmm.
converting the deals for us, right? And so
Yep.
I think we only like to start talking about selling, right, once it's adding value. And so this aha
Yes.
moment has happened with all of these customers, I would say.
Wow. That's impressive, and congratulations and kudos to you and your team. So
Yeah.
it's absolutely great. So coming more, so you said that you're building like one of the products which effectively does the LLM thing, is the functional aspect of it. So how does it do that? So let's say if I run a regression and there are like 10 failures,
Mhm.
what's the next step the tool would do? Like what's the process with that?
Yeah. I'd like to talk about it a bit more, but this product is a little bit more in like beta slash like stealth
Sure.
right now. Well, I wouldn't say beta, but
Okay.
stealth a little bit.
I see.
So I can't
I
really
see.
talk about the internals or like exactly how it works right now.
Sure. Mhm.
But I hope that makes sense. But yeah,
Yep.
hopefully soon we can talk like publicly about what we're doing with this. And
Sure. No, that makes absolutely sense. Yep. And thank you for being very honest
yeah,
and
yeah, of
open
course.
about it. Yep. Yep. Cool. So, all right. So, coming back to Silimate, I know that you're working as a CTO there. Do you have plans to expand? Are you currently hiring? And what do you look for if you are, hiring new engineers, new hardware people there? So, yep.
Yeah, absolutely. We are in fact hiring. We are
I
growing the
see.
team. So we just moved. We're in the process of moving to a larger office, which can fit more people. It's still on Castro Street in Mountain View, and
Hmm.
yeah. So we're both hiring full-time founding engineer roles. And so the idea of a founding engineer is you work very closely with me. We like to keep the team very small, right? And we want to
Sure.
keep it very lean so that we can move quickly.
Hmm.
Um, you'd be working very closely with me on developing our products out, both our functional and PPA side. And
Yep.
what we look for is we look for people who are first principles thinkers, right? And what that means is like you're very scientific in the way that you think about things. You think about things like, okay, how can I build the simplest possible solution and then only optimize it, right?
Yep.
And then, how do I architect things in a way that, allows for future improvements, but without adding too much overhead, right? And so we look for people who have this sort of first principles mindset, right? And I think that's probably one of the most important things in terms of skills. We're looking for people who have, like, ideally some chip background, right? It's a lot easier to work in the space, I think, when you have some some experience or some interest in the VLSI space, or with front end design, especially in chip design.
Yes.
And so we're looking for that, but then also having a very strong coding background. I know that's a very hard thing to find, and but it's we're very picky about I think who we take, and we want a team that's full of very motivated individuals who have a very strong interest in the problem space. I think that's super important to us, right? It just makes coming to work a lot easier, especially I've noticed this for myself. I come into work like energized every day because the problem I'm working on is so cool, right?
Yeah, I absolutely agree on that. I mean, it's very cool. It's very innovative. Something which is right out of the box, never been done before. So I'm excited for you guys. I'm excited for others who have been here also.
Thanks for having me.
So it's absolutely amazing, and I absolutely agree with the thought that you would want people who are excited about this problem, who are who think from first principles, because at the end of the day, you would want someone who is who can think through the problem statement and actually go ahead and implement it. So you don't need someone who can just, I mean, yeah, you would definitely do need people who are doers, like who can just go and
100%.
implement things for you guys. And when you say like it's coding, like does it generally mean like the front end for the RTL design and verification coding, or is it more to do with the software background side of things, like integrating stuff and
Yeah, it's mostly
writing?
software. So we don't do like design services or anything like that, where we,
I see.
are directly writing RTL or verification. Instead, having an understanding of those and being able to, validate that outputs from our tool, or, inputs to our tool are correct, right?
Yep.
Is very important, right? And understanding the process of, like, how do you debug a chip, right, is very, it's very useful to come in. We obviously don't need, a person coming in to know everything, right?
Right. Right.
That's not realistic, and we, especially if we were looking for someone who also has a coding background, I think we're looking for people who are excited about the problem. I think that's super important to us.
Yep.
Rather than people who are just excited about AI or stuff. We want people who are excited about chips, and I think this is something something that is very important to us.
No, I absolutely agree. Yep. Great. And one of the things which I actually wanted to ask before, but unfortunately did not get a chance, was to, did you have any, or generally all of these big chip companies, they are so used to working with different EDA tools like the top three and all of that. They are mostly reluctant to try out newer tools, newer methodologies, and especially if it is to do with AI, because for them IP is critical. They don't want any of their data to be leaked out. And with AI, that a lot of those are like cloud solutions. I assume that you would actually go and do the on-premise installation of your tools and stuff like that. But have you had challenges uh, converting those clients into actually just uh, at least trying out the product, because that could also take a while to give them access to their on-premise servers, and then you going and then figuring things out. So all of that, I believe it would be like a challenging thing to probably figure out. So how was your experience with it?
Yeah, it's definitely kind of a challenge that I didn't anticipate, but it makes a lot of sense, right? Chip companies have to be very risk averse because to
Right.
these things, because of how expensive it is to do a retape
Yep.
out, and they have a lot of expenses that go into the other EDA tools that they're buying from Synopsys and Cadence and Siemens, right?
Right.
And
Right.
so we've managed to work around these with all of our customers so far, and
Mhm.
the way we do it is we try to, like, in cases where the infrastructure is the problem, we just provide it, right? And so we just give them, we provide like a server or something, right? That helps the
Mm.
customer just get started and do an eval, right? Just do an eval, and then after that we can, if it works and the value is clear, right, then it's very
Right.
easy to go and figure out the right deployment strategy for the long term, contract.
Right. That makes sense. Yep. So yeah, one of the last questions which I have for you, Akash, is you are at the forefront of AI meets chip design meets EDA and all of that. So according to you, where do you think like AI would have the opportunity to make most impact on hardware design process slash verification slash EDA thing? Where do you think AI would create the most impact, and why do you think so?
That's a great question, and I really think it's across. Well, firstly, I think front end design is a really good place to focus, right?
Hmm.
For a lot of reasons, especially for a startup. So, firstly, I think it's going to be across the stack. I don't think there's an
Sure.
area of the stack where it's not going to touch, right? And
Sure.
it's going to revolutionize in some way. You see that in the more of the back end side. You see things like DeepMind working on and Google working on reinforcement learning for like placement and stuff like that. I think it's going to touch every layer of the stack. We've been really focused on this concept of spec to RTL, and this is sort of I think I mentioned before our North Star, where the
Hmm.
idea is that you have an AI that takes your design specification and is able to create both design collateral and then also your test bench collateral, right, from
Yep.
that, and sort of works in a feedback loop between these three things where it's able to iterate. Of course it's never going to get everything right the first time, and it's going
Right.
to unearth, like I said, hidden assumptions that you didn't know you needed in the spec, right, in order for everything to work, and will help you
Hmm.
sort of formalize everything about your design in a very in a way that makes sense and can be validated by human by looking at it as well, because humans at the end of the day will need to continue to validate that everything is going to work, right, and that all of the applications are running the way they're supposed to, right, etc.
Right.
Before you do a tape out. But
Hmm.
basically having, I think the holy grail is basically to have the three, the written spec, the design verification collateral, and the RTL all
Yep.
talk to each other sort of in a feedback loop where they kind of
Hmm.
are in sync, right? And a big problem that you see at companies is sometimes there's an update in one and then it doesn't really
Yeah.
propagate.
Yep.
And the long-term goal is really to have these in sort of a loop with one another. And I think that would speed up, chip design from like
Hmm.
12 months to maybe, to 12 to 16 months to maybe like 1 to 2 months, right? And now it's similar to the length scale of a software project, which is a really exciting opportunity, I think,
Right.
to
Right.
see this. So that this is where we're going. Of course, we're staging it, right? We're trying to solve
Hmm.
individual problems within that alignment, right, between
Yep.
designs, alignments between specs, right, and the designs. So our PPA, PPA tool helps you find bottlenecks in your PPA that isn't meeting your standard.
Hmm.
Looking at bugs that are finding, and we're going to keep expanding the pie from there.
Right. No, I agree. So I think what you said makes sense that eventually the time to get the chip out would probably gonna shrink to a few months, which would have like the side effect of a lot of different software companies trying to come up with chip design
100%.
for their own specialization, their own softwares, and probably make things better as we go, because obviously it's faster in hardware and it's more performant, and if you have the hardware to do that thing which you're trying to do in software, so it does
Totally.
make sense.
Yeah.
So
Bringing down the non-recurring engineering costs is going to
right,
also bring a lot of new players into the space. And there's a lot of
absolutely.
companies that want to design chips, but it's too expensive.
Yep.
And
Mhm.
we're going to see that change soon.
I agree, and I can't wait to see that happening.
Yeah, me
Yeah,
too.
and I absolutely hope that you guys are there, and I wish you and your co-founder and all the best, and the entire Silimate team all the best. Uh, Hope you guys build exciting AI based products, and yeah. Thank you for taking out time once again, talking through
Thank
your
you,
journey,
Rahul.
talking
Really
about
appreciate
Selena. Yeah,
really
it was
appreciate
great
it.
talking to you. Yep.
Yes.
Yep. Thank you so much. Yep.
All right.
All right,
Thank you
have a
so
good
much.
day. Bye.